Hi, my name's Jack Adaletta, and this is my MQP, FATE, a Fourier-Accelerated Tensor Engine. The major contributions from this project are, there's a US patent pending on the technology through WPI. I wrote a 140-page MQP report detailing all of my findings. I wrote a 10,000-line C++ neural network library from scratch, and I will make public so that WPI students can build their own custom models with custom kernels. And I received a collaboration request from an OpenAI researcher to pursue further work in this area. Let me show you. FATE is a Fourier-Accelerated Tensor Engine. My name is Jack Adaletta. This project was advised by Professors Basima Islam and Professor Ukahan Guler. FATE is a dot product accelerator for neural networks. A dot product is the sum of products of components of two vectors. Neural networks use dot products when a weight matrix is multiplied by a column vector, and each row of the weight matrix is multiplied by that column vector to produce a neuron activation for the next layer. The problem with current hardware for our neural networks is power and cost. GPUs require intricate logic circuits to perform the dot products and arithmetic required for neural networks. Digital logic requires high power and many transistors to perform computation and move data. FATE addresses both computation and data movement with analog circuits. FATE performs a dot product differently than digital. Using sine waves of integer multiple frequencies, 1 omega, 2 omega, 3 omega, and 4 omega, FATE will encode a vector as the amplitudes of each integer multiple sine wave and then sum them to encode a vector as a continuous time signal. For two vectors encoded in this way, when multiplied and integrated, the dot product is the result. This Fourier dot product method has two steps. One, encoding vectors as sums of sine waves, involving generating sine waves and then multiplying those sine waves by the respective vector component, and two, multiplying and integrating the continuous time encodings of vectors. To generate sine waves, FATE smooths square waves. An input clock into a frequency divider produces integer multiple frequency square waves, which are low-pass filtered and smoothed to produce integer multiple frequency sine waves. These sine waves are multiplied using analog multipliers by the respective component of vector A and summed using a standard summation amplifier as shown on the right. This same circuit is repeated for vector B. The analog multiplier required for this circuit requires 12 transistors. The multiply and integrate stage first multiplies the time encoding of vector A and B using the same 12 transistor analog multiplier. This product is integrated using an integrator op-amp, and an NMOS device resets the capacitor of the integrator. At the period, the voltage on the output is the dot product. To compare against digital, I designed, synthesized, and laid out a dot product circuit for two 4-length dot products with 4-bit precision. This circuit required roughly 5,000 transistors. Compared to FATE, which requires one multiply and integrate circuit for the dot product, requiring 12 transistors for the multiplier and 20 for the op-amp. That's 32 transistors for FATE against 5,000 in a digital design. FATE also wins on data movement. Once FATE encodes a vector as a continuous time signal, only 2 wires are required to route that signal in a circuit. Meanwhile, a GPU will have to use a number of bits equal to the length of the vector times its bit precision. In this case, FATE reduces data movement by 10x. As FATE uses more carrier frequencies and higher bit precision, this reduction will grow. I simulated this circuit in Cadence Virtuoso to answer the question, does FATE accurately produce dot products? The two sources of inaccuracy in FATE are smoothing square waves into sine waves, whether that process is perfect, and the multipliers, which impart some inaccuracy when they are modeled as a times b plus some small value k times a squared plus that same k times b squared. Ideally, k is 0. The circuit schematic I tested is shown in the bottom left. On the right are simulated results showing the relationship between the expected magnitude of an input dot product and the measured voltage output, demonstrating a highly linear response. This circuit works. I analyzed the effects of both inaccuracies on neural networks using a custom C++ neural network library. On the forward pass, I replaced every multiplication in a dot product with the polynomial multiplication representing the analog circuit. I grid searched over different CNN configurations and values of k and found that a little nonlinearity when k is small, can actually enhance CNN performance and improve F1 score. Fate has the ability to improve neural network performance. To conclude, I defined a Fourier dot product algorithm. I implemented a circuit and cadence that can do dot products with high accuracy. I made a C++ neural network library to prove that it works, and I have a patent pending on the technology. Thank you for watching.